Hi everyone, welcome to Vedantu NEET English. I'm Diksha Kaushal, your chemistry master teacher. And yes, very good evening everybody, very good evening. So, yes, today we are going to do P block group number 15 and group number 16. Okay, so are you all excited? And from these two groups, the questions are frequently asked, right? There are so many exceptions. I'll also tell you that exceptions that are not there in your NCERT, but they're actually somewhere hidden, right? So we'll talk about everything, and yes, this lecture is going to be enough for your P block, right? First part, second part, and tomorrow on Sunday at 5 p.m. I am going to take the third part of this lecture to make a sequence, right? Okay, so today we will do group number 15 and 16. Tomorrow we are going to resume this class, and that will be group number 17 and group number 18, and our topic is going to be finished. Okay, yes everybody, am I audible? Am I visible to everyone here? Am I audible? Am I visible? So last time what I observed that you guys were not able to see the pages because of the brightness, because of the white page here, right? That is why today now we will have black pages only, right? So that you are able to see this, right? So I understood that problem in last class. So that's why this lecture and tomorrow's lecture is going to be in this format. Yes, everybody, I can't see your energy in the chat box. Where is your energy, guys? Where is your energy? Where is that Josh? Where is that energy? Everybody, P block has 3 parts, guys. Only 13 and 14 is not in your syllabus. 13, 14, 15, 16, 17, 18, you have to do all these 3 parts. Okay? Yes, audible, visible. So everybody, green hearts in the chat box so that we can start with the session. Yes, so that we can start with the session. Yes, no worries. I am here to understand you only. Na? That's my duty. That's the work. That's the duty of a teacher. And duty of a student is to respect the teacher, and how you can show your respect by engaging in the session, right? Okay, be engaged in the session. Try to write something whenever I'm talking to you. Say something in the chat box, whatever I am asking you, right? Okay, give the response in the chat box, because that's the only way I can understand that what you guys are thinking. Okay, so let us start the session without wasting any time. So here we are talking about, they are saying that in class 11th you have studied the class 11th portion that we studied group number 13 and 14, that was in class 11th NCERT, right? So class 11th you have learnt that the P block elements are placed in group 13 to 18, right, of the periodic table. Their valency varies from S2 to NP1 to 6, right? That is the valency, right, except helium, which is completing its duplet. The properties of P block, like that of others, are greatly influenced by atomic sizes. We have seen ionization enthalpy, electron gain enthalpy, and electron negativity. The absence of d orbital, now they are saying that first period elements were like boron, like carbon, they were behaving differently as compared to other elements of that group. Why? Because they didn't have any d orbital. Even the vacant d orbital was not present there. So the absence of d orbitals in second period and presence of d and dnf orbitals in the heavier elements, because of the presence of d and f orbital, right, as we go down the group, because of that there are some changes in the trends that we have observed because of inert pair effect, has significant effect on the properties of the elements. In addition, the presence of all the 3 types of elements, whether you talk about metals, metalloids, and non-metals, they are present in P block, right? Had diversification in chemistry of these elements. Having learned the chemistry of elements of group 13 and 14 of the P block of the periodic table in class 7th, you will learn about the chemistry of group number 15 and group number 16. So now let us talk about group number 15 here. Okay, let us start with the group number 15. Yes, very good evening students, very good evening Ganga, Raju, evening Star, Roshni, Madhumati, Drishyani, Dhanushari. Madai, very, very good evening. So here we start our chapter. I think this is better, no? Yeah, even I am feeling that this is much better, right? So group 15 includes nitrogen, phosphorus, arsenic, antimony and bismuth. These are the elements of group number 15. Nitrogen, it's like this. Na pee aisi sharab bai, right? Na pee aisi sharab bai, right? So now this is nitrogen, phosphorus, arsenic, and antimony and bismuth, right? Okay, nitrogen, phosphorus, arsenic, antimony and bismuth. These are the compounds of group number 15, right? So you will see some similarities with group number 13 itself, right? As we go down the group, there is shift from non-metallic to metallic character. As we go down the group, we know that down the group, the metallic character will always increase, right? Okay, so down the group, non-metallic character will decrease, right? So there is shift from non-metallic to metallic through metalloid character. Nitrogen and phosphorus are non-metals. These two are non-metals. If you talk about arsenic and antimony, they are metalloids. These two are metalloids. And if you talk about the last one, that is bismuth, it is a non-metal, right? So bismuth, sorry, that is a typical metal, right? Because down the group metallic character is increasing, no? So these two are non-metals. Then you have metalloids. This is your metal, right? Molecular nitrogen. Now we are talking about mainly the compounds that we see, right, are of nitrogen and phosphorus. Hardly you will see bismuth, antimony, arsenic in your compounds, right? You will hardly study those compounds. So for you, nitrogen and phosphorus are very important, and the exceptional trends are very important here. So molecular nitrogen comprises 78% of our atmosphere. In our atmosphere, we have molecular nitrogen by the volume of the atmosphere. In the earth crust, it occurs as sodium nitrate, NaNO3, called chili salt peter, right? So this is also important to know that in our atmosphere, how in our nature, in our earth crust, how it occurs, right? Then there is potassium nitrate, that is called Indian salt peter, right? So that is potassium nitrate. Instead of sodium, you have potassium here. It is found in the form of proteins in plants and animals. So in proteins, right, in the proteins we have amino acids. In amino acids we have nitrogen. So it is found in proteins and plants and animals. Phosphorus occurs in minerals. Now we are talking about proteins. Basically they are made up of amino acids. In amino acids we have NH2 group, that is nitrogen is present. Let us talk about phosphorus. Phosphorus occurs in minerals. Which minerals? Of the apatite family. And let's talk about in which minerals it actually occurs. So firstly you have Ca9PO46 or .CaX2, which is called fluoropatite, right? Which is called fluoropatite, right? Which are, now here for example, you have, these are the apatitores, apatite family, right? Where you have this X, right? If this X is replaced by fluorine, if this X is basically halogen, that can be fluorine, chlorine or OH, right? If it is fluorine, then it is called fluoroapatite, right? Which are main components of phosphate rocks. So in rocks where you have phosphate, it is the main component. Phosphorus is essential constant of animal and plant matter. It is present in bones as well as living cell. In our body also it is present, right? So phosphoproteins are present in milk and eggs. When we drink milk, when we eat eggs, because they are not vegetarian, right? Milk we call it vegetarian, but actually yes, it is vegetarian obviously, but it is derived from a cow, right? So it is basically coming from an animal only. So that is why it has that kind of proteins. Arsenic, antimony and bismuth are found mainly as sulfide minerals, right? The important atomic and physical property of this group element along with their electronic configuration are mentioned here. And from this we are going to draw some important points from this table itself, right? So as you can see, the atomic number 7, then 15, then 33, 51, 83. This we have done according to the magic numbers. You can make the atomic numbers, right? Next is atomic mass. So as you can see here, down the group, atomic mass is increasing, right? So atomic mass is definitely increasing down the group, right? Then you have electronic configuration. For nitrogen, you have 2p3, right? Here you have 3p3, 4p3, 5p3, 6p3, right? But can you see one thing here? In arsenic, you have 3d10, right? In antimony, you have 4d10, and in bismuth, you have 4f and 5d. That means here you have inert pair effect in arsenic, bismuth, and antimony, right? Okay. Next is ionization enthalpy. As you can see, ionization enthalpy is decreasing here without any exception, right? It is simply decreasing, right? If you talk about ionization energy 1, 2, 3, it is increasing, 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 increasing. That means till now we have not seen any exception here. The size is increasing down the group. Ionization energy is decreasing down the group. That was actually the general order of size and ionization energy, that size should increase and ionization energy should decrease, right? Now, next is electronegativity. As you can see here, electronegativity has a trend here. It is firstly decreasing, then almost it is same, right? But yes, we can say that electronegativity increases along the period, decreases down the group. So it is also making that same kind of similarity here, right? Now, covalent radius. Now, obviously, if size is increasing down the group, right, then obviously radius will also increase down the group, right? So these are all the normal things, right? These are all not the exceptions. Now, in group number 15, this is 15. In group number 15, you have not seen any exception till here. But definitely there are exceptions somewhere else, right? In boiling point, melting point, there are exceptions. And in this case, especially hydrides are asked, right? Okay, hydrides, halides are asked to you, right? So if we talk about radius also, it is basically what is happening. It is firstly, it is increasing. Then again, it is constant, then it is decreasing, right? Now, ionic radius, they will not ask you. They will simply ask you the simple size, right? So now let us see the melting point here and the boiling point here. Okay, here so you can write electronegativity decreases. Now what about melting point? Can you see the order here? Can anybody tell me the order of melting point here? Melting point order, anybody in the chat box? Melting point order, this is now tell me what is the melting point order here. Anybody in the chat box? 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 What is a melting point order? Hello, hello, hello. Good evening, beta. Good evening. So as you can see from here, this is the maximum. So arsenic has the maximum. Then you have antimony, arsenic, then antimony. After that, what you have? After that, you have bismuth. After that, you have phosphorus. Then minimum is for nitrogen. So this is the order of melting point, right? That is why it becomes important for you, because it has a very different order, right? So if you talk about boiling point order, that is also different, right? It is not a very smooth order, right? What we can see from this order, that maximum is for this antimony, then you have bismuth, right? Then you have arsenic, then you have phosphorus, then you have nitrogen, right? So this is basically the order, boiling point and melting point order, right? That is minimum for nitrogen, phosphorus, and here it is changing, it is having variations over here. It is having variations over here, right? Okay, it is having variations over here. Right, everybody? SB, then BI, then AS, yes. SB, then BI, then AS. And melting point is ASSB. Wait a minute. AS, then SB, then BI. Yes. Arsenic, it is... Okay, right? So this will become the order here, right? Okay. Okay, so this will become the order of melting point and boiling point. That has a very unique order. That is why this becomes important for you. And this also has been asked to you in the exam. Next, density, they will not ask you the density, right? Eventually, it is increasing only, right? So, it is increasing only. You can say that down the group, it increases. Electronegativity decreases, right? If you talk about the size, it obviously increases, right? That is why mass also increases, right? Mass also increases. Ionization enthalpy decreases, right? So everything is same. It's just that the order of this melting and boiling point is different, right? So now let us see what is the reason behind that. The valence shell electronic configuration of these elements is ns2np3, that we know. The s orbital of these element is completely filled, ns2, then you have np3, this is completely filled, and p orbitals is half filled, right? So whenever you have any half filled configuration, it will give it extra stability, right? It will give it extra stability, right? Covalent and ionic in a particular state, if you have talking about in a particular state, radii increases in size down the group, right? Both are increasing. There is a considerable increase in covalent radius from nitrogen to phosphorus. However, from arsenic to antimony, only a small increase in covalent radius is observed. This is due to the presence of D and F orbitals in the heavier member. Basically, what they are saying, that if you talk about the radius here, if you talk about the size here, it is increasing down the group, right? It is increasing from 14 to 30, right? There is change. Then you talk about, wait a minute, where is the radius? Where is the radius? This is the covalent radius, right? Yes. So from 70 to 110, there is like a large change. Then there is small change, and very small change. From here, we can see that this is definitely increasing. But here you have a large change. But after this, you have very small change. Very small change. Very small change. Can you tell me what is the reason behind that? Because as I have told you in the electronic configuration, here you have 3D, 4D, 4F, 5D. And the shielding effect is like this. S, then P, then D, then F. Now the shielding effect of D and F orbitals, electrons are not very strong. That is the reason that the size will increase, but to a very small extent it will increase. Now from antimony to bismuth, there is very small change as compared to others, because here there is addition of F electrons also, right? So the inert pair effect is responsible for this thing, right? Next we have ionization energy. Now they are saying that ionization enthalpy decreases down the group, right? There is no exception here. Trend is not exceptional, right? Due to gradual increase in the atomic size. As size will increase, right, it will be very easy for the outermost electron to leave the atom. That is why ionization energy will decrease down the group, right? More is the size, less is the ionization energy that is required, right? So because of the extra stable half-filled p orbital electronic configuration, you have NP3 from where, because it is stable. Now if you take out electron, it will become NP2, right? Now this is the reason, as compared to other group, its ionization energy is more, right? So half-filled p electronic configuration, smaller size, ionization enthalpy of group 15 is much greater than that of group number 14, right? That means you can say that ionization enthalpy of group 14 is basically more than ionization enthalpy, or you can say group 15 is more than ionization enthalpy of group 14. Why? Because here the configuration is NS2NP3. Here it is NS2NP2. So it is easy to take out electron from this side, right, as compared to this side, because it is already a stable configuration, because it is already a stable electronic configuration, right? Okay, the elements in the corresponding period. Now you can write all these things right somewhere in your NCERT to make it easy for you. The elements in the corresponding period, the order of successive ionization enthalpy is definitely, now when you talk about the first ionization enthalpy, we are taking out electron from a neutral atom. Second, we are taking the electron from a cation. Third ionization energy, you are taking the electron from a 2 positive ion. It is even more difficult. So that is why this will become the successive ionization energy order. The electronegativity value, as we know that down the group it is going to decrease. In general, decreases down the group with increasing atomic size. However, amongst the heavier elements, the difference is not that much pronounced, right? That is why I was telling you that focus on the table here, right? So as you can see the table here, the electronegativity, it is 3, then it is decreasing from 3 to 2, right? Then from 2.1 to 2, then 2.0 to 1.9, then from 1.9 only, it is almost same only. So down the group it is definitely decreasing, but nitrogen to phosphorus there is a large decrease. After that it is almost constant only. The decrease is either very small or it is almost constant only, right? All these elements of the group are polyatomic in nature. That means if you talk about dinitrogen, that means nitrogen exists as N2, right? Nitrogen will exist as N2, right? Phosphorus will exist as P4, right? It will not exist as di, it will exist as tetra. Dinitrogen is a diatomic gas while all others are solids, right? Now phosphorus is a solid. Metallic character increases down the group. We know that if you talk about the metallic character here, non-metallic character decreases and metallic character increases down the group, right? So what we can say, increases down the group. Nitrogen and phosphorus are non-metals, very important, right? They are non-metals. This we have done before also. Arsenic, antimony are metalloids and bismuth is a metal. This is due to decrease in ionization energy. Now they are saying why it is so, right? The same concept that I told you yesterday, right? So when your size, down the group size is increasing, right? Down the group size is increasing. Size increases means the nucleus, the positive charge on the nucleus, how much far away it is from the electron. It is because size is more, so it is far away from the electron. That is why the pull of this nucleus to that electron will be less. That is why it is easy to lose the electron. So metals are those which lose the electron. Non-metals wants to gain the electron. That is why metallic character is increasing down the group, because size is increasing. Ionization enthalpy is decreasing. That is the reason. Okay, so this is due to decrease in ionization enthalpy and increase in atomic size. The boiling point in general increases from top to bottom. Now this is the exception that we have, right? Here is what we need to focus on. Now what they are saying, that the boiling points in general increases from top to bottom in the group, but the melting point increases up to arsenic and then decreases up to bismuth, right? So now they are talking about the boiling and the melting points, right? The boiling point in general increases from top to bottom. If you talk about in general here, top to bottom boiling point, it is increases, right? It's na P. It's like this. The order should be like this, right? The order should be like this. But here we can see the change in the order, right? If you talk about the boiling point, it is increasing, but in this case, you can see the difference, right? This is the difference that you can mark here, right? In general, it is increasing, but there is one exception that you can see here, right? Okay, there is one exception that you can see here, so underline this exception here. In general, you can write that it is increasing, but melting point order should also be like this, but it is totally like too much messed up. Here, our bismuth was supposed to be the last, but it is at this point, and then you have antimony, and then you have arsenic, right? So here, this thing is very important for you, right? This order is totally changed, right? Okay, so this is what they are saying here. This is what they are saying here, that melting point increases up to arsenic, then decreases up to bismuth, right? Increases up to arsenic and then decreases up to bismuth. As you can see here, melting point will increase up to arsenic. After that, it will start decreasing, right? It will increase to this point, then it will start decreasing, right? You can also mark a point here. It will start increasing up to arsenic, then it will start decreasing, right? This is the thing that you have, right? Okay, that was, these two are very important, okay? These two orders are very important for you because these are the only exceptions that you have here. Now, oxidation state and trends in chemical reactivity. That was about the different exceptions, right? There are only two exceptions in melting and boiling point. Now, let us talk about the oxidation states and trend in chemical reactivity. So, the common oxidation state of these elements is plus, minus, so always it will have, right? Because NP3 means it can lose 3 electrons and become minus 3. It can gain 3 electrons. It can lose, wait a minute, it can gain 3 electron. It can lose 3 electron. It can lose 5 electron, right? Here, after gaining, it will become NP6, NS2, NP6. Here, it will become NS2, right? After losing, here it will become nothing, right? Here, it will be NS0, NS0, NP0, right? Because it has lost 5 electrons here, right? So, these are the 3 oxidation states in which it can exist. The tendency to exhibit minus 3 oxidation state decreases down the group. As I told you that lower oxidation state, right? Lower oxidation state will, firstly, if you talk about the lower oxidation state, I will be talking about plus 3 and minus 5, plus 3 and plus 5. If you talk about minus 3, that is the ability to gain the electrons, right? The ability to gain the electrons. So, they are saying it decreases down the group due to, why? What is the reason? See, nitrogen is very small in size, right? So, that is why it is easy for it to gain the electrons because the size is small, right? Less repulsions it will observe. But as you go down the group, there will be more electrons involved, right? More electrons will be there, right? That is why more repulsion to the incoming electron it will have. That is the reason down the group it is difficult to gain the electron, right? So, tendency to exhibit minus 3 oxidation state decreases due to increase in size and metallic character. Now, metallic character increases mean it wants to lose the, it has the tendency, it wants to lose the electron down the group. Bismuth wants to lose the electron. You are saying you have to gain the electron. It will say, I don't want to gain the electron. If I am saying I have good tendency to lose the electron, why you are asking me to gain the electron? I don't want to. That is why minus 3 oxidation state decreases down the group. Okay, right? This is a very important thing. In fact, last member of the group, bismuth, right, hardly forms any compound of minus 3 oxidation state. The stability of plus 5. Now, this is the higher oxidation state. As I told you, lower oxidation state. Always remember this one thing. Lower oxidation state, its tendency increases down the group. Always in all the groups. Increases down the group. Lower means all the positives we are talking about. So, lower is plus 3. Plus 3 will increase down the group. Plus 5 will decrease down the group. Right? So, plus 5 oxidation state decreases down the group. The only, well, why, what is the reason? Can you tell me the reason behind that? So, now, if you talk about a compound, right, I am just taking, this is 2 electrons here. It has 3 electrons here, right? So down the group size is increasing. Earlier the size was this much, then this, then this. Now the size is this much large. Okay, now the size is even more large. Now what will happen, right? At this point it will have d electrons also, it will have f electrons also. That is why this last electron will be very much attracted towards it, right? And here you have two things. One is S, one is P, right? One is S, one is P. Now S is even more closer to this positive nucleus. That is why it is difficult to lose the electrons of this S orbital, right? That is why it is difficult to lose. Now are you able to understand this thing, what is happening? Down the group I told you that size is decreasing, right? Down the group size is decreasing. This was the size, then this is the size, then this is the size. Now I am saying down the group size is decreasing, right? For example, here the size is even more decreased, right? For example, here this is your bismuth, right? In bismuth I am saying you have F electron also, you have D electron also, right? You have D electrons, then you have S electrons also, then you have these P electrons, right? You have 2 electrons in S and 3 electrons in P. Now I am saying that this D and F has poor shielding effect. So the electron that are outside this thing, that are the outermost electrons, they will be attracted towards this nucleus inside, right? So that is the reason, because of their poor shielding effect, the outermost electrons are attracted. Here P is more, S is more closer, that is why it will have more attraction. That is why down the group it is difficult for the S orbital to lose the electron, because it has more attraction. If you talk about antimony, right, in antimony, or if you talk about bismuth, not bismuth, if you talk about antimony and arsenic, right, here you will have only D electrons, right? Here you will have only D electrons, so it will be intermediate, right? Whether it can lose, it can also not lose. So it can, but it has less choice of losing S orbitals because of this D electrons that are having poor shielding effect, right? So that is the reason that down the group lower oxidation state increases, right? So decreases down the group. The only well characterized B5 compound is BIF5. That is the only compound that has bismuth in +5 oxidation state. The stability of +5 oxidation state decreases and that of +3 increases due to inert pair effect. What is inert pair effect? It's the same thing that I taught you here. This is inert pair effect, right? Due to poor shielding effect of the orbitals, the outermost electron is attracted towards the nucleus. That is inert pair effect, right? Down the group. Nitrogen exhibits +1, +2, +4 oxidation state. Right now they are saying nitrogen, sometimes it can exhibit also +1, +2, +4 oxidation state. Also when it reacts with oxygen, right? It can represent these kind of oxidation states. Phosphorus shows +1 and +4 also. That means nitrogen shows +1, +2, +3, +4, +5 and -3. Nitrogen shows 6 oxidation state. Phosphorus shows +1, +3, +4 and +5, right? Okay. In case of nitrogen, all oxidation state from +1 to +4 tend to disproportionate in an acid. Now this is important, that in case of nitrogen, if it is showing +1 to +4 oxidation state, it is going to dissociate, because nitrogen, everybody, nitrogen is more stable in higher oxidation state, because the upper elements are more stable in higher oxidation state. Nitrogen is more stable in higher oxidation state. That is the reason when it has lower oxidation state, it will disproportionate in acid. For example, you have HNO2, right? Here the oxidation state is 1 + x - 4 = 0, x is equals to 4 - 1, that is 3, right? Here oxidation state is +3, right? You can write it here, oxidation state is +3. Wait a minute, let me write it here. Oxidation state is +3. Here it is 1 + x - 6 = 0, x is equals to 5. So you can write oxidation state is +5 here. which is a stable oxidation state for nitrogen, right? And here it is +2 oxidation state. So disproportionation means when it is going under oxidation and it is also going under reduction. It is also going under reduction. There is also increase in oxidation state. There is also decrease in oxidation state. That is called disproportionation, right? So in some oxoacids, yes. Okay, so this reaction, it will go under disproportionation, right? Now, next is, similarly, in case of phosphorus, nearly all intermediate oxidation state disproportionate to +5 and -3, both in alkali and acidic medium, right? That means they are saying that in case of phosphorus also, if you have intermediate states like +2, +3, +2, so it will not exist, like you have +4, you have +3, right? I'll write the intermediate states here. Like you have +2, not +2, 2 it will not exist, +3, +3, +4, right? Because phosphorus will exist in which oxidation state? +1 also, right? +2, yes. So it can be +1, +3, +5. Then it will get converted to +5 and -3 oxidation state. Okay, +5 and -3 oxidation state. Okay, yes everybody, yes everybody. Now, however, +3 oxidation in case of arsenic, antimony, bismuth becomes increasingly stable with respect to disproportionation. Now we know that down the group +3 oxidation state will increase, so there will be no disproportionation here, right? Nitrogen is restricted to maximum covalency of 4 since only 4 orbitals are available for bonding. Now we have seen this in organic chemistry as well. I told you so many times that nitrogen can never form pentavalent. It can never be pentavalent. Like whenever, if nitrogen is forming 3 bonds, then it is having neutral. If it is forming 4 bonds, there will be one positive. 5 bonds is not possible only. What is the reason? Reason is because it has only 5 orbitals. No, 2 orbitals, 1 orbital of this, right? Then you have these 3, right? That is why it has only 4 orbitals. That is why only 4 bonds are possible here, right? The heavier elements have vacant d orbitals. As we go down the group, right, like phosphorus, phosphorus is existing in PCl5. Can you tell me why? Nitrogen, NCl5 does not exist. PCl5 exists. You can say it like this here. NCl5 does not exist. PCl5 exists. Why? Because nitrogen does not have no vacant orbital, no vacant d orbitals. But phosphorus has vacant d orbitals, and the extra electrons can lie in this extra vacant d orbitals, right? So here you can say that the heavier elements are vacant d orbitals in the outermost shell, which can be used for bonding and hence explain their covalency as PF6 negative also, right? PCl5. Why this exists? Because of the vacant d orbitals, right? Okay, yes guys. Next is anomalous behavior of nitrogen, right? Nitrogen, why it is behaving very differently, right? So let us see. Nitrogen differs from rest of the members of the group due to small size. See, it is same as boron and carbon. We have seen that why boron has anomalous behavior, why carbon has anomalous behavior. Same thing we will apply in nitrogen as well. Nitrogen having small size, higher electronegativity, right? The electronegativity is very high, right? Then we have high ionization enthalpy. Down the group it will decrease. Small size, high electronegativity, high ionization enthalpy, and very important, non-availability of d orbital is the reason for nitrogen to show anomalous behavior as compared to the other elements of the same group, right? Nitrogen has unique ability. Now, what are they? Firstly, we know the reason. These all are the reasons why it is showing anomalous behavior. Now here, in which it is showing anomalous, what kind of anomalous behavior it is showing. So nitrogen has unique ability to form p-pi bond. You have never seen p double bond p, right? No, you have not seen. Phosphorus is forming single bonds only, sigma bonds, but nitrogen forms 3 triple bonds. It forms triple bonds with other nitrogen. So multiple bonds it can form. So that is because of it has unique ability to form p-pi multiple bonds. And here p-pi, d-pi, no. Why? Because d-pi, it does not have any d orbital, right? That is why p-pi with itself and with other elements having small size and high electronegativity. For example, with carbon it is forming C triple bond N, right? How it is forming C triple bond N? It is forming triple bond with the carbon. Reason is its ability to form p-pi bonding, right? With oxygen also it can form the p-pi bond. Oxygen also does not have d orbitals, okay? This carbon and oxygen also do not have d orbital. That is why here also they are not forming p-pi, d-pi, p-pi only, right? Heavier elements of this group do not form p-pi bonds as the atomic orbitals are large and diffuse, that they cannot have effective overlapping, right? So as I told you yesterday also, heavier elements will not be able to form because the shell will increase, the size will increase, and pi bond is due to sideways overlapping. So sideways overlapping in a large shell will be very difficult, right? Okay. Thus nitrogen exists as diatomic molecule with triple bond, right, where one S and 2p between two atoms. Consequently, its bond enthalpy is very high, right? Is very high, that is 941.4 kilojoule per mole. On the contrary, phosphorus, arsenic, antimony form single bonds, as you must have seen, PP, AS, then SP, which bismuth forms a metallic bond. Bismuth is a metal, so it will form metallic bonds, right? Metallic bonds in the elemental state. However, single NN bond is weaker than the single PP bond. Now, this is important. Single NN bond, why it is weaker, right? Because of high interelectronic repulsion of non-bonding electron. So just imagine this thing. This is nitrogen, and these are the lone pairs. These are the lone pairs here, right? This is nitrogen. It is forming how many bonds? Yes. This is your nitrogen, and these are the lone pairs. Wait a minute, let me draw it again. This is your nitrogen, it is forming a single bond. We know that whenever it is forming a single bond, there must be other bonds also that it is forming. And here you have a lone pair. Because of the small size of this thing, it will be very close. It may be like this. It will be like this, right? It will be like this. And here you have the lone pairs. Now, the lone pairs will have the repulsion, right? Now, because of the small size of nitrogen, two atoms are very close to each other. The bond length is very near to each other. Bond length is very small. Because of this, there will be, it looks like some guy I have drawn here, right? So it's chemistry ma'am drawing, right? So this is how chemistry ma'am will draw things, right? So here this lone pair and this lone pair will repel each other. And because of that repulsion, this bond will become weak, right? But if we talk about phosphorus here, this is phosphorus. Now what will happen? These are the lone pairs, this is the lone pairs. Because phosphorus is having more size, so the atoms will be slightly away from each other. Because of that thing, the lone pair will not have that much repulsion. Hence, the interelectronic repulsion of the non-bonding electron, that means lone pair they are talking about, right? Lone pair, owing to the small bond length, right? There will be more repulsion. As a result, the catenation tendency is weaker, right? Hence, a result, this NN bond is weaker as compared to PP bond. Hence, the catenation tendency of nitrogen is weaker. Carbon had a good catenation because it didn't have any lone pairs, but nitrogen has lone pairs, right? Group 15 will always have lone pair, okay? So another factor which affects the chemistry of nitrogen is absence of d orbitals. As I told you, absence of d orbitals, it will not be able to expand the covalency in the valence shell besides restricting its covalency to 4, right? That is why always I tell you nitrogen only forms 4 bonds to the maximum, and if it is forming 4 bonds, it should have a positive charge. Nitrogen cannot form d pi p pi, reason being it does not have d electrons only as a heavier element, right? Can, for example, this thing they are talking about, that here phosphorus is able to make a d pi p pi bond with oxygen. Oxygen will have p pi, phosphorus will have here d pi, because phosphorus can have d pi electrons, oxygen cannot have. Oxygen, again, it is a first element, it does not have any vacant d orbitals. If you talk about this thing again, right, this carbon will have p pi and this will have d pi, right? So phosphorus and arsenic can form d pi bonds also with transition. Now we are talking about d pi p pi. Here d pi p pi is possible. Guys, are you able to understand this thing? How I am saying directly that d pi p pi is possible, d pi p pi is not possible. First element of all the p block elements, first element will not have any vacant d orbital, right? So there will be p only possible, right? Okay, so here also with oxygen or with carbon, it is forming p pi d pi. Now, if it wants to have d pi, then it should form the bond with the d. That means the transition elements, right? So phosphorus arsenic can form d pi bonding, but in that case it should be with the transition metals when their compounds like this arsenic with this C2H5 thrice, right? And arsenic, this is phosphorus, this is arsenic, and here acting as a ligand, right? When they act as a ligand, basically this phosphorus, then this phosphorus will make a bond with the ligand, right? Which, wait a minute, they're acting as a ligand, no? Yes, this phosphorus is acting as a ligand, right? It is donating the electrons to the metal, and we know that whenever there is coordination bond, it has d orbital. Phosphorus also has d. In this case, it can form d pi. Okay? Okay, guys, everybody in the chat box, tell me if you are able to understand this or not. Is there any lag? Everybody? Rathi, Sumana, Nissan, Nandu, Ganga, Raj, Banot, yes, okay. Yes, ma'am, clear? Okay, perfect. Now, next thing is reactivity. It's a reactivity towards hydrogen, right? So, if you talk about the reactivity towards hydrogen, all the elements of group 15 form hydrides of the type. Now, this is very important because it is frequently asked, right? These kind of things are frequently asked from hydrides, right? So if you talk about the hydrides, all the elements of group 15 forms hydrides because group 15 is usually existing +3 and hydride is H negative, so it will become EH3. This kind of hydride will be formed, and you must know ammonia, NH3, PH3, ASH3, SBH3, BiH3. So these are the hydrides, right? Some of the properties of these hydrides are shown. These hydrides show regular, from hydrides, it's very important question can be asked. The hydrides show regular gradation in their properties. The stability of hydrides decreases from this to this. Thermal stability here they are talking about, right? Here they are talking about thermal stability. From here also the question are asked. It is decreases from nitrogen to bismuth, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character means to reduce someone else, right? So of the hydrides increases down the group, right? Ammonia is only mild reducing agent, while bismuth is the strongest reducing agent. We'll talk about everything here. Among the hydrides, basicity also decreases in this order. So all these, this first one, thermal stability, then you have reducing character, then third is the basicity, right? These three are important factors for you, okay? These three are very, very important factors for you, okay? So now, I'm going to write down this thing here, right? Firstly, we will see the table, then I'm going to write down all these properties and their trends here, right? So firstly, let us see that. If you talk about the melting point of hydrides, everything is important here. If you talk about the melting point of hydrides, it is decreasing, then increasing, then it is increasing, right? So boiling point, it is decreasing, it is then again it is increasing, then again increasing, right? So melting and boiling point have the same trend. We will write the trends, just give me some time, okay? Then here you have angle, this is the bond angle. Bond angle is also asked to you. Bond angle is also very important, right? Bond angle is also very important, that it is decreasing, and then it is decreasing only. If you talk about the delta H formation, right? Delta H formation, so they will not ask you that, right? Dissociation they can ask you, right? Dissociation, this is definitely decreasing and decreasing, right? Now, from here, I am writing some trends here, okay? I am writing some trends here. First thing is, or should I write it on the next page? I'm going to write it here only, right? So first thing I'm going to write is, first trend is the bond angle, right? The bond angle, okay? The bond angle or stability or basicity. Anything they can ask you, it will have the same trend, right? So here what they have written, basicity also decreases, na pi aisi sharab bihari. So it will be na pi. Okay, so the hydride, it is decreasing in this order. Even if they can ask you anything here, okay? It is decreasing in this order. I'll tell you the reason also. First, you just see the trends, okay? If they ask you bond angle, if they ask you stability, if they ask you basicity, you will have the same trend. You can see this from here as well. This is the bond angle, it is decreasing here, right? If you talk about the thermal stability also, where it is, thermal stability decreases, right? It is also decreasing. Basicity, it is also decreasing. So these three things are decreasing here. That is why I am writing it here, that these three things are decreasing here. Then you have the second point, that is reducing power to reduce someone, or acidity. Now, reducing power and acidity, right? So these are the same things only, right? So let's talk about what is the order here of reducing power and acidity, as they have written it here only, right? So where it is written, the reducing character of hydride increases. Ammonia is only mild reducing agent, while bismuth is the strongest reducing agent. So that means it is increasing. So it will be NH3, then you have PH3, then you have ASH3, then you have, it is increasing, right? ASH3, then you have SPH3, then you have BiH3, right? So that becomes the second order. Third order is melting point and boiling point, right? So here you can write, just give me a second. Boiling point has a very weird order. Here you can also write melting point. That will also have the same order only, right? Melting point. right? Let us see the melting point order here. Melting point, it is, wait a minute, what we have written, that melting point of this NH3 is maximum, then it is decreasing. What about this thing here? It's maximum, then it is decreasing, but then it is increasing again. So it will not be the order. Just give me a second. Let us write the order here of melting point. Because we need to follow in Google, you will see different orders. We need to follow what is there in the NCERT, right? We need to follow that thing only, right? So here it is nitrogen, it is very large, then it is decreasing. Firstly, you have nitrogen, right? Firstly, you have nitrogen, right? Then you have, after nitrogen, you have antimony, right? Then you have, I think, arsenic, right? Then you have arsenic, then you have phosphorus. Then you have arsenic, then you have phosphorus. Now, what about the boiling point order? What about the boiling point order? Boiling point is maximum is for SB, no, maximum is for bismuth, then you have antimony, then you have nitrogen, then there is a reason why nitrogen is in the middle, okay? Then you have arsenic, then you have phosphorus, right? This is the order. So I'll write BSB, BISB. Boiling point is, boiling point order is, this is the last from hydrides. This is the last trend that you need to remember. First is bismuth, then you have Sp, then you have nitrogen, right? Then you have arsenic and phosphorus. Arsenic and phosphorus, right? Now let us see what is the reason behind all these trends, okay? Everybody, now let us see what is the reason behind all these trends. Okay, guys? Okay, guys, everybody. So this is the trend that we can see from the table, right? Now, write down these trends because these are directly from your NCERT, right? And the trends mentioned in NCERT are the correct ones. Don't go for Google trends, right? What is mentioned in the Google, right? Go for what is mentioned in the NCERT, even if the trend of Google is right, okay? You see that, ma'am, this is given by some brilliant scientist in some foreign book. It is written, right? Ma'am, is this correct? Yeah, that might be correct. But the answer is that in whenever you get bonus marks, you get that if you give the answer that is mentioned in the NCERT, that is regarded as a correct answer, okay? So in trends, especially students get confused because they see it from Google and then they write the same thing in the exam. But NEET, they will NEET and JEE, what they will prefer, that is from NCERT, whether it's right or wrong, okay? So that's what I'm saying. Now, here these are the trends. Now let us see what is the reason behind that. See, if you talk about the reason here, if you talk about the bond angle, firstly let us see the reason for the bond angle, right? Bond angle, why it is maximum for nitrogen? Because it's small size, more repulsion, what is happening? Angle is increasing, right? Because it has bond pair repulsion is more, that is why angle is increasing, that is why it is decreasing like this. That is the reason for bond angle. If you talk about the thermal stability, right? So definitely when you talk about NH3, right? So basically what is there, no? So NH3 is having hydrogen bonds, right? So nitrogen, it is electronegative, right? So it will form hydrogen bonds, right? So it will form hydrogen bonds with its own molecules. That is the reason down the group electronegativity is decreasing, right? So that is the reason it is having more thermal stability, right? And the other reason that you can say is hydrogen, it is in 2p, nitrogen also in 2p. So it is 2p 2p interactions, overlapping is really good here. That is why it is more stable. Here it is 2p 3p, here it is 2p 4p, 2p 5p, 2p 6p. That is why down the group overlapping will decrease and hence the stability will decrease, right? Okay, this is the same reason for your basicity. Now basicity and acidity are opposite to each other. Now let us understand by reducing power, right? If you talk about the reducing power means to reduce something, right, and to itself get oxidized, right? So basically reducing power and acidity are the same thing only, right? So that is why here it is going to increase down the group, right? Okay, so reason is simply that acidity, because of the hydrogen bonds here, it is very difficult for this NH3 to lose that hydrogen, right? Basicity, you know one thing, okay, just tell me one thing. What is basicity? You can understand this by concept of acidity also, by basicity also. If you want to understand this with the help of concept of basicity. Basicity means availability of lone pair, isn't it? It is availability of lone pair. Now, if your lone pairs are available to you, that means if the size is small, lone pairs are more like available to you. If the phosphorus, the size of the atom is very large, so lone pair are less available because atom is very large, so the lone pair is that thing only. Lone pair is two electrons only, right? So in small size, the electron are more available, right? So that is why here the basicity decreases down the group because the size will increase down the group. The lone pair availability will be less down the group. Okay, understood? That is the reason for the order of basicity, right? Now basicity is opposite of acidity. You can also understand by this thing, or you can also understand that this NH3 is going to make hydrogen bonds, right? So it is very difficult to lose the hydrogen here because acidity is losing the hydrogen, right? That is the reason it will increase down the group because there is no hydrogen bonding down the group, right? So that is the reason of acidity and basicity, and melting point and boiling points are defined experimentally, so you can easily understand that. Yes, everybody? Okay. Okay. So just remember, after this, so they can't ask you anything. Hydrides, they will ask you from this thing only, right? Okay. Now, next thing is reactivity towards oxygen. So now this is E3 positive and you have O2 negative. So it will be E2O3. This kind of oxide will be formed. This is what they are saying. This is E2O3. If you have E5 positive, O2 negative, then you will have E2O5 kind of oxide that they have mentioned here. The oxide in the higher oxidation state of the element is more acidic. They are saying that oxide which is there in the higher oxidation state of the element is more acidic, right? Higher oxidation state is more acidic. Can you tell me why it is more acidic? Can you tell me why? Now, higher oxidation state means +5 oxidation state. Lower oxidation state means this oxidation state. Now, they are saying that if in the higher oxidation state, the oxide, we know that it is the upper oxides, right? They are more acidic in nature. Why? Because down the group, we know that metallic character increases. Metallic oxides are basic in nature. And down the group, +3 oxidation state is more stable. Here, non-metallic character is more, right? That means acidic oxide is more. And upper elements have +5 oxidation state, higher oxidation state is more stable, right? So the acidic character decreases down the group, right? So that is the reason acidic character also decreases down the group. You can write it here. Acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic because lower oxidation state, you can also write it here, are more acidic as compared to higher acidity, right? So that of arsenic and antimony, which are amphoteric, right? and the lowest, that is the metal oxide, will be basic in nature, right? Okay. Next is reactivity towards halogens. So from halogens, what we can see, these elements react to form NH3. Okay, one thing I forgot to tell you, that why here NH3 is in the middle. Why here NH3 is in the middle? Because of the hydrogen bonds, right? Because of the hydrogen bonds, the strength of this hydrogen bond is strong. That is the reason it will be in the middle, right? Maximum will be this one, then this one, right? Then you have, wait a minute, arsenic. Yes, then nitrogen will be somewhere here. So basically it's like this. Right? So this nitrogen will jump to this side, right? The boiling point order should increase down the group, right? It should increase down the group. So nitrogen should be minimum, but it will jump in the middle because of the hydrogen bonding. So this question also they can ask you, right? This question also they can ask you, that why it is so, right? So here, reactivity towards halogens. So if you talk about halogens, these elements react to form two series of halides. See, if your metal is in +3 oxidation state, it will form this. Metal is in +5 oxidation state, it will form EX5. Nitrogen does not form pentahalide. Have you seen NCl5? No. You have seen NCl3, NF3. But NCl5 we have not seen. So it will not form pentahalide because it does not have vacant d orbitals. Pentahalides are more covalent than trihalides. All the trihalides of these elements except those of nitrogen are stable, right? Nitrogen trihalides are not stable, except those of nitrogen are stable. That means all the trihalides are stable except for nitrogen. In case of nitrogen, only NF3 is known to be stable, right? Only NF3 is known to be stable. Why? Can you tell me the reason? Why only NF3? Because here also it is 2p, here also it is 2p. So somewhere this becomes stable, but with 2p, 3p overlapping, it is even less stable, right? There's so many factors that contribute to the inorganic chemistry, right? So trihalides except for BiF3 are predominantly covalent in nature, right? So except for, very, very important, this BiF3 halide is ionic in nature, right? Very, very important, right? Others are covalent in nature, right? Others are covalent in nature. Reactivity towards metal. See, metal, we have different metals, right? We have group number 1, group number 2 metals, right? So all these elements react with metal in their binary compounds exhibiting -3 oxidation state. Metals wants to lose. So the counterpart should gain the electron. That is why here these elements will gain 3 electrons. Group number 15 elements will gain 3 electrons. For example, here you have CaN. Now here nitrogen is having 3 negative, calcium is having 2 positive. That is how you have Ca3N2 kind of compound, that is calcium nitride. Here also it is P3 negative. Here also it is As3 negative. Here also it is Sb3 negative, and here it is Bi3 negatives. In all these cases, it is existing as E3 negative, right? It is gaining the electrons, right? Instead of losing, it is now gaining the electrons. Now let us see some compounds. Now the reactions are not that much important for you, right? I'll tell you some of the things that are important. Yes, 2p is more stable. Now let us see that. Okay, one by one we will see everything. Till here, what we have done, that has high probability that they will ask you questions from the trends, exceptions, right? All these cases. From now onwards, there are few points that you need to keep in mind, right? Otherwise, all the reactions are not important because they are not specially mentioned, right? Okay, so now earlier it used to be important, but now it's not that important, right? It is obviously important. Don't say that I'll just skip this. What I mean by is your priority should be those things. These are in addition that you have to do, right? So now dinitrogen, that is N2, is produced commercially by liquefaction and fraction distillation. Liquid dinitrogen distills out, first leaving behind oxygen. In a laboratory, dinitrogen is prepared by treating an aqueous solution of ammonia chloride. This is the equation, right, where dinitrogen is produced. Not important for you. Then small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid. Through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by the thermal decomposition. Very pure nitrogen can be obtained by the thermal decomposition of sodium or barium azide, right? Okay, so this you can remember, that how pure nitrogen can be obtained from the azides. Now let us see the properties here. Properties are important, right? Dinitrogen is colorless, odorless, tasteless, non-toxic gas. It is also there in your Lay's, Kurkure packets, right? It is also there, right? To increase the shelf life of that thing. Now nitrogen atom has two stable isotopes. These are the two stable isotopes of nitrogens. Very low solubility in water and low freezing and boiling points, right? It has very low freezing and boiling points. That is why the nitrogen in the atmosphere will not freeze at like -20 temperature. Our atmosphere will not freeze because maximum we have is nitrogen in the atmosphere. Dinitrogen is rather inert at room temperature, right? Why at room temperature it is inert? That is the reason in our universe all reactions are not happening. In this air also I have nitrogen, but it's not affecting me, right? Why? Because it is inert, right, at room temperature, because of its high bond enthalpy of, this is important, right? It is inert and it is having high bond enthalpy. That is the reason, right? So reactivity, however, increases rapidly with the rise in temperature. When you rise the temperature, now at higher temperature, it directly combines with some metals, predominantly ionic nitrides. Non-metal, it forms covalent nitrides. Now this is also important for you, that nitrogen, when it combines with metals, it will form ionic nitrides. With non-metals, it will form covalent nitrides. Example is lithium, magnesium. It is forming ionic nitrides here, right? Okay, so now here we have, it combines with hydrogen. This is a very, very famous process called Haber's process, right? So here, with when it combines with hydrogen, it forms ammonia. That is very important process called Haber's process, right? Now, here in presence of a catalyst, Haber's process to form ammonia, right? And now what you need to remember is this is exothermic in reaction, exothermic in nature. Here they will not ask you this directly, but they can ask you this applying the exothermic situation in maybe equilibrium, maybe asking you the spontaneity of the reaction. In Gibbs-Helmholtz equation they can ask you, right? So this should be, this little points you should remember, right? Dinitrogen combines with dioxygen to form only at high temperature to form nitric oxide, right? And this is also at a very high temperature. Otherwise, in the atmosphere, we have nitrogen, we have oxygen. If this reaction occurs at room temperature, then our universe will not exist, right? So in our universe, we will have nitric oxide only, but we don't have this. Reason? Because they both are very inert at room temperatures, right? Uses are, the main use of dinitrogen is in the manufacture of ammonia and other industrial chemical containing nitrogens. Calcium cyanamide, it also finds use where inert atmosphere is required, right? Where you require inert atmosphere, even in labs, right? So iron and steel industry, inert diluent for reactive chemicals. Liquid nitrogen, now this liquid nitrogen is so very, very famous, right? So liquid nitrogen is used as a refrigerant to preserve biological materials, food items, and in cryosurgery. This cryosurgery is basically when you have when you want to have the body parts, right, as it is after like a long time also, right? Okay. So preparation not important. Now we have ammonia, right? Reactions are not that important for you, right? So ammonia is present in small quantities in air and soil where it is formed by decay of nitrogenous organic matter, right? So this is your urea, right? From urea it can be obtained. One is Haber's process, other is urea. On adding water to the urea by simultaneous processes, you can have nitrogen gas, right? So this is an organic matter only. On a small scale, ammonia is obtained from ammonium salts decomposed with treated with caustic soda. See, with caustic soda, NH4, this is positive, this is negative, 2 positive, OH negative. So here you will have the formation of NH3, water, and CaCl2, right? Again, this salt with some good base, it can form ammonia, right? Then you don't need to remember the full reactions. Just remember one thing: ammonium salts, right, with base can form ammonia. That's it. Okay. On large scale, ammonia is prepared by Haber's process, right? In accordance with Lee-Chatelain, this is important, right? Because we have seen this in equilibrium as well, right? That is why this paragraph will become important to you. In accordance with Lee-Chatelain principle, high pressure would favor, first is high pressure, right? Would favor the formation of ammonia. Reason, because if you see here you have 4 number of moles, here you have 2 number of moles. High pressure will go to that side which has less number of moles, right? So here it will go to the forward side, right? So that is why high pressure is required. The optimum condition for the production of ammonia are the pressure that is this much, right? A temperature is also very high in this case because it is an exothermic reaction. That is why the temperature is high. And the use of catalysts such as iron oxide with the small amounts of K2O and Al2O3 to increase the rate of attainment of equilibrium. The flow chart of the production of ammonia is shown in figure. Earlier, iron was used as a catalyst with molybdenum as the promoter. So these little things you need to remember for these reactions. Okay. Now this is not important, right? You don't need to go through this, right? So basically it's a process. They have shown you that how Haber's process, you have the formation of ammonia here, right? Okay. Next is properties of ammonia. Properties of ammonia. Ammonia is a colorless gas with pungent odor, right? Very pungent, very stinging to your nose it will have, right? You can easily predict that if something of ammonia that, wait a minute, like if you have ammonia gas in the lab, you can easily say that this is ammonia, right? Very pungent smell, right? So in the solid and liquid state, it associated through hydrogen bonds. We know that it has hydrogen bonds, right? NH3, definitely it has hydrogen bonds. So in case of the water, that accounts for its higher melting point and boiling points than expected. We were expecting it as that it should have, wait a minute guys, wait a minute, yes. We were expecting that it should have low melting points, but because of the hydrogen bonds, it has high, right? Now what is the structure? The structure is trigonal planar. This also we have done in chemical bonding. We have done the structure, no? It will having a lone pair and this is a pyramid that it will form, a triangular shape it will form. So basically it's like this. The geometry is tetrahedral only because it will have sp3 hybridization. But this lone pair, if you talk about the shape, we don't consider lone pairs. So this is a pyramid that it is forming. So that is what is called trigonal pyramidal, right? I smelled in chemistry, yes. It is like even if you are not in chemistry lab, now you are just passing by, you can say that yes, there was one gas, I think that was H2S gas. Oh God, what horrible smell it used to have. Like seriously, when we used to do the salt analysis in the labs, no. So whenever there was some experiment that involved, because if in the compound there is sulfur, so there was some use of, I think that is cancer causing also. So our teachers used to avoid that chemical. I think that was H2S gas only. It was horrible, guys. It was horrible. Like literally, I used to feel like I just want to run out of that lab. Not only in the lab, but also in that corridor, whole corridor, right? The arts and commerce students, they used to look at this, give us these looks at how these guys are standing in the lab. Like it's so stinking. Like seriously, it was horrible, horrible smell it was. So, okay, the ammonia molecule is trigonal planar with nitrogen atom at the apex, right? Nitrogen atom at the, it is 3 bond pairs and 1 lone pairs. Ammonia gas is highly soluble in water in aqueous solution. So it will, what it will form? It will form ammoniated ion, right? So it is weakly basic due to the formation of OH negative. Once you add water into it, the solution will become weakly basic, right? So this is basically your ammonia. Right, next is, it forms ammonium salts with acids, for example NH4Cl, NH4 twice SO4. So with salts also it can form, right? So it can form different things. Now this is very important. As a weak base, it precipitates the hydroxides in case of some metals. Of basically they are saying that you have metal salts with ammonium hydroxide. What they will produce, they will form with this OH, they will have OH, with this OH they will have metal, and then with ammonia they will form the salt here, right? So this is the example that they have given you. It is a displacement reaction, nothing else, right? So here, this is the next reaction they have given with the ammonium hydroxide, right? Okay, so this is ammonium hydroxide, this ammonium hydroxide, this thing they are talking about, right? Next is the presence of lone pair on the electron. So now they are saying that because of the presence of lone pairs, right, they are attracted towards the cations, right? On the nitrogen atom, the ammonia molecule makes it a Lewis base. Why it is a Lewis base? Because it is electron rich. It is electron rich. It donates the electron pair, forms linkage with metal ions. Now, when it donates the electron pairs with the metal ions, right, the formation of such complex compounds find applications in the detection of metal ions, right? So, basically, that is why it is going to form this is called amine when it comes to ligands, right? So, it will donate the electron pair and act as ligands, right? That is how it will form coordination compound, and that is how ammonia also behaves as a good ligand in coordination chemistry, right? So this is giving you a deep blue color, right? Similarly, they are saying that this Cl negative, wait a minute, why we have written it here? Okay, now they are saying that, for example, you have AgCl with NH3. Now what will happen? Again, the lone pairs of this will be attracted towards this this positive ions, right? And they will donate the electron to this positive ion, and hence this compound will be formed along with the counter ion here, right? Okay, so basically coordination, they are all in simple language, they are saying that ammonia behave as a ligand. It can behave as a ligand. Simple way, this is what they are telling you, right? Okay. Okay. Ammonia is used to produce various nitrogenous fertilizers, ammonium nitrate, urea, ammonium phosphate, ammonium sulfate, right? And in the manufacture of inorganic nitrogen compounds, the most important one being nitric acid, right? Liquid ammonia is also used as a refrigerant. Like liquid nitrogen was used, liquid ammonia is also used in the refrigeration process, right? Okay, guys. Okay, everybody. Now let's do the oxides of nitrogen. Anybody? The oxides of nitrogen. One of them is very, very famous. One oxide of nitrogen is very famous. Which is that oxide? What I'm doing now? For example, I started to laugh like a crazy person. You'll say, hey, what you have? Laughing gas or what? Right? So laughing gas. It was also used in Akshay Kumar's movie, Houseful 3 or Houseful. That was actually a very flop movie. But yes, I think in the last climax of that movie, they have used laughing gas. Right? So nitrogen forms a number of oxides and different oxidation states, the name, formulas, everything is mentioned here. Okay? So now, ma'am, from this table, what we need to remember, right? So, see, you don't need to remember these reactions. Okay? These reactions, you don't need to remember, right? You can just go through them once, right? But they will not be asked to you, right? So you can remember the formulas. From formulas, you don't even need to remember the oxidation states. You can calculate. For example, this is 2x minus 2 is equals to 0. So it will be x is equals to 1. Here it is x minus 2 is equals to 0. So x is equals to plus 2. Here it is 2x minus 6 is equals to 0. So x will become plus 3. So you don't need to remember or cram this oxidation state. This, if you have the knowledge, very good, laughing gas. Right? So, if you have the knowledge, then you can easily calculate the oxidation number here. Yes, then physical appearance and chemical. Now, this is important for you, right? Colorless. Now, this is neutral. What about this N2O3? That is a blue solid and it is acidic in nature, right? Then you talk about this thing, that is nitrogen dioxide. Here oxidation number is x minus 4 is equals to 0, that is x is equals to plus 4. What about this one? 2x minus 8 is equals to 0, so x is equals to again 4. 2x is equals to minus 10 is equals to 0, so x is equals to plus 5. Right? So oxidation state you don't need to remember. Just remember it is a brown gas and this is a very important gas. Okay? This is a very important gas. Why nitrogen dioxide is an important gas? Because in practical chemistry, in identification of salt analysis, there are some reactions where the identification is dependent on this gas. It's a brown gas, NO2 gas, right? Then you have N2O4, that is colorless liquid, acidic, right? Then dinitrogen pentoxide is colorless solid, which is acidic in nature. Okay? Yes, everybody. Yes, everybody. Yes, everybody. Very good. Now, next is the structures. Now, structures you need to remember. This again can be asked in chemical bonding. Now, if they, as I told you, they have not mentioned all these compounds in your syllabus, right? They have not mentioned that they are out of your syllabus. They have not mentioned that they are in your syllabus. So for that, we need to be safe, right? So if they ask you these structures, they can easily say that structures, so you need to know from chemical bonding, right? Then what you will say, right? They can say that this is not a part of P block. You should know that what are the oxides. It's a very simple thing. You have done redox reactions. Can't you calculate the oxidation state? Don't you remember the names? It's a basic thing for chemistry students, right? So you need to remember the structures here. This we have done in chemical bonding, right? Very important. Some of them having odd electrons like this. It has odd electrons. Can you see? This had odd electrons. This we have done in exceptions. Odd electrons. Here you have on this oxygen, you have 5 electrons. This nitrogen, you have 3 electrons. So odd electrons. Here also you have odd electrons. Odd electrons. So this also can be asked to you. N2O3, very important, right? NO2, again it is having odd electron, it can be asked, right? Then you have N2O4, then N2O5, right? So these all are very, very important for you, right? Okay, okay guys, try to make these structures with the help of Lewis dot structures, okay? Have you done Lewis dot structures with me or not, everybody? Newton, yes. Nandu, oxytocin, Divya, Dhanushri, Dhanushya. Yes, Roshni, do you remember we have done this part? We have done how to make the structures, right? So try to do it yourself with the same. If you don't remember anything from chemical bonding, just type the lecture chemical bonding Lewis dot structure by Diksha ma'am, Vedantu NEET English. You will get that, right? Now from that, revise that and try to draw these structures, because you don't need to remember these, okay? So odd electrons are the exceptions, right? Rest you can form with the help of Lewis dot structures, and some of them though I have already made in Lewis dot structures. Okay. Nandu, I have completed organic chemistry. I have completed organic chemistry, bacha. Nitrogen forms oxoacids such as H2N2O3, that is hyponitrous acid. Then you have HNO2 nitrous acid, HNO3. Amongst them, HNO3 is the most important because it is a very good oxidizing agent. It's a very, very good oxidizing agent, right? In a laboratory, how nitric acid is prepared? It is prepared by heating NaNO3 and H2SO4, not important. On a large scale, it is prepared mainly by Oswald's process. Now, this method based upon a catalytic oxidation of NH3 and giving it oxygen from the air. Then you have this catalytic oxidation. Then you have the formation of nitrogen oxide, that is NO. From there, you again it is forming NO2. Then after adding water, it is forming your nitric oxide, which is a very, very good acid, right? An oxidizing agent, right? Okay. Next is properties. Now let us see the properties. As I told you, preparation is not important for you, right? Let us see the properties here. It is colorless liquid, laboratory, this, you don't need to remember this. Now, HNO3 exists as a planar molecule. What is the structure? Important, very, very important, right? Structure of HNO3, it's you have NO with nitrogen. It is having 3 bonds with oxygen, right? Then 1 bond with OH, right? So it is a planar structure. It is a planar molecule with the structure as shown. In aqueous solution, nitric acid behave as strong acid giving hydronium ion and nitrate ion. So in water, it will give hydronium and this nitrate ion, and it's a very good oxidizing agent as well, right? So if you talk about here, is a strong oxidizing agent, very important, right? Is a very good oxidizing agent. Attacks most metals except noble gas, very, very important, right? Except noble metals such as gold and platinum. For gold and platinum, you need aqua regia, right? Do you remember what we did in smaller classes? You need aqua regia if you want to attack gold and platinum, right? This is a very strong oxidizing agent, but it will have no effect with gold and platinum. The products of oxidation depends upon the concentration of the acid, the temperature and nature of the material undergoing. So if you have copper, it can oxidize this copper. If you have again this copper with if you have dilute and concentration, see, if you have diluted, right, and if you have concentrated, right, in that way it will have the different products, right? So when you have dilute, it will have NO as a byproduct. When you have concentrated, it will have NO2 as a byproduct, right? Zinc reacts with the dilute nitric acid to give N2O. With concentrated, it gives this. Now with zinc, it is going to give you NO2 with dilute nitric acid, right? You have zinc. With the zinc, if it is having dilute, it will give you NO2. Where is N2O? Sorry, N2O. With the concentrated, it is going to give you NO2. These things are, the whole reaction is not important, okay? These things are important, that with zinc, when you have dilute, when you have concentrated, what it is going to give you. Some metals, for example, do not dissolve in concentrated nitric acid because of formation of passive film oxide on the surface. Concentrated nitric acid also oxidizes non-metals and their compounds. Iodine is oxidized to iodic acid. Right now, what it can do? It can oxidize iodine to iodic acid. It can oxidize carbon to carbon dioxide. It can oxidize sulfur to H2SO4. It can oxidize phosphorus to phosphoric acid. Right? Okay, these all things it can do. Now, this is iodine to iodic acid, carbon to carbon dioxide, sulfur to H2SO4 and phosphorus to H3PO4. Now, this is important, right? This is important that how it can oxidize which thing. Only these four reactions, that iodine to iodic acid, right? Carbon to carbon dioxide, sulfur to H2SO4, phosphorus to H3PO4, right? Next is brown ring test. This is also part of your practical chemistry, right? So let us go through this. The familiar brown ring test for nitrates depends on the ability of Fe2 positive to reduce nitrates to nitric oxide, which reacts with Fe2 positive to form brown color complex, right? The test is usually carried out by adding dilute. For example, you have Fe2 positive ions. So what will happen? The test for nitrates depends on this, reduces nitrate. So this is your nitrate. It will get reduced to nitric oxide, right? So nitrates to nitric oxide. Firstly, though, if you have Fe2 positive. Next, this nitric oxide with further, it will reduce, which reacts to form a brown colored complex. It will further react with that complex to form a new complex, which is like a brown ring, right? So it is forming this kind of complex, which is having a brown ring, right? So it will tell you that you have Fe2 positive ions here, right? Okay, understood? Understood, beta? This is important. Brown ring test is important for you, right? It is used for the identification of Fe2 positive ions. Firstly, it will reduce, oxidize nitric acid, not reduce nitric acid to nitric oxide, right? Then you will have this nitric oxide will further convert this compound to a brown complex. That is called identification of that brown ring. It's like a ring only in the tube, right? It's not basically that kind of ring, right? It's in the tube you will see a ring kind of situation, right? Because you will see that if you see that tube above it, you will feel like there is some kind of circle rings here, right? So that is why it is called brown ring. Not exactly, it is not like a ring, okay? Then the major use of nitric acid is in manufacture of ammonium nitrate for fertilizers, other nitrates, explosive, pyrotechnic techniques. It is also used in preparation of nitroglycerin, trinitrotoluene and other organic nitro compounds. Other major uses is pickling of stainless steel, etching of metals, and an oxidizer in the rocket fuels. So these are the uses, right? Okay. Okay, guys. Now let us talk about phosphorus here. Okay. Shall we talk about phosphorus? Everybody, shall we talk about phosphorus? What you want me to explain again? The brown ring. Brown ring, if you have Fe2 positive, firstly the nitrate ion will be converted to nitrogen oxide, which further will react with the complex and it will convert it into a brown ring. When you have that brown ring, you can say that there is Fe2 positive ions in the solution, right? Basically, this test is used for the identification of Fe2 positive ions, right? Okay, yes. Phosphorus, it is found now. Firstly, for phosphorus, you need to understand the two allotropic forms of phosphorus. One is white, other is red and then black. Now, white phosphorus is translucent white waxy solid. It is poisonous, insoluble in water, but soluble in carbon disulfide, glows in dark, right? It dissolves in boiling with NaOH solution and is inert atmosphere, giving PH3. That is a phosphine gas, right? Okay. Now, from here, what you need to remember, that is a translucent white waxy solid, right? It is insoluble in water but soluble in carbon disulfide, right? Now, white phosphorus is less stable, right? It is less stable. Therefore, it is more reactive than the other solid phases under normal condition because of angle strain in the P4 molecule, right? Now, if you talk about this one, its structure is like this. Because of this kind of structure, it has more angle strain. Because of this structure, it is more reactive and it is very less stable, right? So you just need to remember that white phosphorus is more reactive as compared to others, right? Where angles are only 60 and it readily catches fire in the air and become P4O10. Reactions you don't need to remember. White phosphorus is more reactive, less stable, right? Then if you talk about red, it is obtained by heating white phosphorus at this, right? If you even heat white phosphorus, you will get red phosphorus, right? When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed, right? Now, from white you have red, from red you have black. Now, red phosphorus possesses iron gray luster. It's like a iron gray luster, right? It's odorless, non-poisonous and insoluble in water as well as carbon disulfide, right? It is both insoluble in water and carbon disulfide. The red phosphorus is much less reactive than white. Now, this is important. It is less reactive and it does not glow in the dark. Just remember the difference point here, right? What is the difference point, right? Okay, this is white phosphorus. Red phosphorus has this kind of structure, right? So because there is no bond between this P and P, it has less angle strain, right? Okay. It is polymeric, consisting of chains of P4 tetrahedral linked to each other, right? Third one is black phosphorus, has two forms, alpha black and beta, right? Two forms, it has alpha and beta, right? Alpha black phosphorus is formed when red phosphorus has, now this statement, just remember this statement. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803. This is alpha, right? It can be sublimed in air and has opaque monoclinic rhombohedral crystal. This you need to remember. It does not oxidize in air. Black phosphorus is prepared by, beta black is prepared by heating white phosphorus at 473 Kelvin under high pressure, right? This is your beta black is formed. It does not burn in air up to 673 Kelvin, right? Okay, the crux of this thing is white is most reactive, then you have red, then you have black, right? Black is having alpha and beta. Alpha is formed at 873 Kelvin. This is 473 Kelvin, right? Sorry, it is 803, right? So that is the thing that you need to remember here, right? This is more reactive, then this is less reactive, right? Why this is more reactive? Because it has angle strain. Just remember few points from this theory part, right? Preparation again not important for you. You can just go through this once in the laboratory. It is prepared by this and that, right? So now when pure, it is non-flammable but becomes inflammable owing the presence of P2H4 and P4 vapors, right? When it is in a pure form, it is flammable, but it will become non-inflammable, but after that it will become inflammable. To purify, it forms impurities, it is absorbed in HI. This all is not important for you, right? Then you can remember the phosphine here, right? So it is colorless. Let us talk about the this phosphine gas here, right? So just remember some points of this phosphine gas, right? So it is colorless gas, rotten fish smell, very bad smell it will have, highly poisonous. It explodes in contact with traces of oxidizing agents like HNO3, Cl2 and bromine vapors. These are very good oxidizing agents, right? So phosphine gas is very reactive towards these oxidizing agents, right? Then you need to know is phosphine is weakly basic, right? And like ammonia gives phosphomium compounds with acids, right? Then you have, yes, just remember few points about phosphine gas. Then the spontaneous combustion of phosphine is technically used in Holmes signals. Containers containing calcium carbide, calcium phosphide are pierced and thrown in the sea when the gases evolved burn and serve as a signal. So basically they are talking about to give signals because it's a very reactive gas. No, that is why to give signals it has been used, right? Again, now you have phosphorus. Then you have phosphorus trichloride. Now again, trichloride, you need to remember the structure here of trichloride, right? So it forms two type of halides. One is PCl3 and then there is PCl5. Both are important for you. Now PCl3 is obtained by again Cl2. If you give it more, now how PCl3 is also formed by this reaction, right? Now what is the properties of PCl3? It is colorless oily liquid. Hydrolysis in the presence of moisture. When you have moisture, it will get hydrolyzed to give you an acid. It reacts with organic compounds containing OH groups such as CH3COH, C2H5OH. We know that these reactions we already know. These reactions we have already done, that it will replace this OH with Cl, right? It will replace this OH with Cl. This is how it will react, right? It has pyramidal shape is important. It has a pyramidal shape. Can you tell me what is the reason? Again, the same reason here. It is having tetrahedral geometry. It is having a lone pair. Lone pair we don't see. That is why in the end it will have a pyramidal shape, right? So it is having a pyramidal shape as shown. Which phosphorus is sp3 hybridized? Definitely because it has one lone pair, 3 sigma. So it is sp3 hybridized, right? Then phosphorus pentachloride, structure is very important here, right? Phosphorus pentachloride is prepared by reaction of white phosphorus with excess of dichloride. Now this line you can remember that it is prepared by white phosphorus with excess of dichlorine, right? So then you have PCl5. It's also prepared by action of SOCl2 on phosphorus, right? Again, you can prepare this. Now properties is yellowish white powder it is. PCl3 was colorless oily liquid. This is yellowish white powder, right? Very what I can say, I don't know the word for that, but it's a very pale yellowish kind of thing, right? So in moist air, it hydrolyzes to POCl3. This reaction is again important. This reaction is also important, right? These two reactions are important for you, right? You can remember these two reactions, right? So PCl5, if you give it water, it will get converted to POCl3, right? POCl3, adding more water, it will get converted to a very important acid, H3PO4, that is phosphoric acid. Important acid, H3PO4, right? Okay. Okay, guys. Now, they are saying very important reaction. Now, this is very important. Why? When you heat it, it will give you PCl3 and Cl2. What is the reason behind that? Just give me a second. What is the reason behind that? Anybody in the chat box? Anybody in the chat box? Now I can't find that structure. Okay, so I'll give you just one example here. Basically, it is having a trigonal bipyramidal structure, right? So, in one trigonal, that means in one plane, it will have a triangle kind of bond which is at 120 degree with each other. Then there will be one bond that is here, one bond that is here, one bond here, one bond here. And this three bonds will be in one plane. Now, this will be in one plane only. Now, this is not in one plane. It should be in one plane at 120 degree angle. So, the other two bonds that are on this above and below axis, they are not very strong bonds. That is why when you heat PCl5, you will get PCl3 and Cl2. It reacts with organic compounds containing OH group very easily. Again, it will replace this OH with Cl. Finely divided metals on heating with PCl5 give corresponding chlorides. So when you have finely divided metals, right, it will give you corresponding halides, right? Okay. Did solid PCl5 of hybridization? Wait a minute, what you just said? Hybridization, it is 5, no? So it is sp3d, okay? Now, this is the structure, right? This is the thing what I was talking about. This thing is very important, right? Very important page, right? It's a very, very important page. It's used to, it is used in the synthesis of some organic compounds, that is these two. It's gaseous. Now, this is the structure. This whole lie in one plane. This is trigonal, and this is above and this is below, right? So, in the gaseous and liquid phase, it has trigonal bipyramidal structure. The three equatorial bonds. So, these three are the equatorial bonds which are strong, but the axial bond is weak, right? While the two axial bonds, now this one and this one are the axial bond. This and this, these two are the axial bonds. Pairs suffer more repulsion. Now, we know that axial pair will suffer more. Now, exactly what will happen, right? Now, this one axial that is above, here you have three trigonal bonds, right? So, these three trigonal bonds will repel this axial. That is why it will face repulsion. And the one that is below, it will also have, this is the above trigonal plane, right? This is the above. This one more which is above. Okay, wait a minute. There is one more which is above. So, it's like this. Right, so this is my hand is like you have three atoms that are 120 degree to each other. This is above, this is below. Above and below are the axials, right? So this hand will repel, that means these three trigonal planar bonds will repel this axial. That means in this trigonal planar, it's like this, it's like this. These trigonal will be here. Right, so they will repel this axial and this axial. That is why it will become really weak, right? Okay, okay, understood? Now, what will happen here? This bond will break, this bond will also break here. That is the reason we are saying that when you heat PCl5, it will get heated and it will give you these two bonds will break. So they can also ask you that in PCl5 when you heat it, which bond you will break, axial or equatorial. So axial bond will break here, right? So that is why this thing is important for you. They can ask you this thing, right? Then in the solid state, it exists as ionic solid. Now very important. In the solid state, it is existing as this kind of solid, PCl4 positive, PCl6 negative, right? In which the cation is tetrahedral and the anion is octahedral. This is in the solid state. That was in the aqueous or gaseous state, right? Okay. Now we have oxides of phosphorus, right? So basically you are going to form the oxides. Phosphorus form number of oxoacids, right? And here oxoacids play a very, very important role here, right? So let us see the oxoacids. The composition of oxoacids are interrelated in terms of loss and gain of water, molecule and O atom. Let us see, these are your oxoacids, okay? These are basically your oxoacids. So this is hypophosphorus acid. Wait a minute. Here you don't need to remember this preparation, right? This you need to remember. This you need to remember. The formula you need to remember. The name you need to remember. So all these things are important. Why I am saying these are not important for just P block, right? They can ask you the same thing throughout your chemistry section. This can be asked, right? Throughout your chemistry section, right? Okay? Yes. Okay. Okay, Ansari, I feel NCERT knowledge is less, that because I am teaching you from NCERT only, right? So now this is hypophosphorus, right? If you talk about let us see the structure firstly. Okay, let us see the structure, right? Okay, so basically you need to also know the structures here. One thing remember, always have P double bond O. Always have P double bond O, right? So for example, you want to draw the structure of H3PO4, right? So what you do, draw P double bond O. Now you are left with 3 hydrogens and 3 oxygen. So you can write 3 OH here. So that will be the structure, right? That is the structure of orthophosphoric acid. Now you want to draw the structure of H4. Let us draw this structure, that is H3PO3. Now again P double bond O, that is the first task to do. Then 3 bonds we are left with. And we are left with here 3 hydrogens and 2 oxygens. That means 2 OH it can occupy. And now we are left with just 1 hydrogen that can be occupied on this place. Right, so that is your structure for H3PO3. Right, now if they are asking you the structure of H3PO2, they ask this in N factor. That's why I am drawing this for you. Right, when you calculate the valency factor, N factor, you need to know the structures of phosphorus, oxoacids of phosphorus. Right, this is H3PO2. Again P double bond O. Right, now you have 3 bonds. PO we have already used, so you are left with only 1 oxygen. That 1 oxygen we have used here. That means now you are left with 2 hydrogens. So that means 2 hydrogens will be here. That is the structure for H3PO2. Right? Okay? Understood? You don't need to cram this. These 3, so we are like easily we can draw these 3. P double bond O, then 3, because phosphorus can form 5 bonds. So rest of the thing you can just see that what we are left with. Right? Okay. Next we have H4PO, H4P2O7. 2 phosphorus you have. Each of them will have a double bond. Right? Now you are left with which thing? You are left with 2 phosphorus already gone, 2 hydrogens on, 2 oxygen already gone. You are left with this thing. Now here it will have 2, and there will be 1 bridge here. That bridge will be of oxygen. So now you are left with 4 oxygens and 4 hydrogen. That is why 1 OH here, 1 OH here, 1 OH here, 1 OH here. Right? Okay, this is how you draw the oxoacids. Okay, guys? Yeah, inorganic is always boring. Right? So this is how you draw the structure of oxoacids, right? So now we are still left with some other structures as well, right? So now these are the big structures. This though hardly they will ask you, right? You have HPO3 thrice, right? 3 phosphorus you have. Now it is in the cyclic structure. This you have to go through first, right? So this is in the cyclic structure. Now here you have 3 hydrogens, 3 phosphorus, and you have 9 oxygens, right? So now what will happen? You will firstly have a 6-membered ring of these 3 phosphorus and 3 oxygens. Then you are left with 6 oxygen and 3 hydrogens, right? That we will use. So 3 phosphorus and 3 oxygen are in this cyclic ring, right? Now we are left with 3 hydrogen and 6 oxygen. That means from here we can have 3 OH. Now we are left with 3 oxygens that will have a double bond, right? So here you will have 3 oxygen which will have double bond, right? And 3 OH that will be present on each phosphorus. Students, this is just a way to remember the oxoacids, right? Okay, just a way to remember the structure of the oxoacids. Right, just remember, this is a cyclic structure. HPO3 thrice is a cyclic structure, right? Okay, this is basically polymer of what we have done before, right? So this is HPO3N. If you have thrice, then it is cyclic. Now here what you are going to do, basically what we did before, right? So you have this phosphorus, one double bond O here, then you have one OH, one oxygen. See, oxygen will be in the bridging state. Oxygen is in the bridging state, right? One oxygen is in the bridging state. You are left with HPO2, right? So here you have used one phosphorus also. If you talk about this thing, this is basically HPO3. This is what they are talking about, right? So one oxygen is in the bridging state. Now you are left with one OH from this unit HPO3. P double bond O you have already used. One oxygen is in the bridging state. Now you are left with one OH that you can draw here, right? That you can draw here. Again, one more oxygen is in the bridging state, and this will start repeating itself, right? Okay, understood? Understood? What is the unit here? This is the basic unit, HPO3. This is a monomeric unit. This is the monomeric unit. This is the monomeric unit of this polymer, right? Again, this is repeating itself. This thing is repeated n times. Okay? Okay, guys. Guys, okay. Okay, chalo. Now let's come to this table, right? You need to know the name, general name, and here the other name of these acids when you talk about oxo. Oxo, see, it will have hypophosphorus, orthophosphorus, pyrophosphorus, hypophosphoric, orthophosphoric, pyrophosphoric, metaphosphoric, these kind of acids. So as you can see here, if you talk about anything, let us talk about orthophosphorus. If you remember what is orthophosphorus, hypo will be one less than that, one less oxygen. So if you remember the formula of hypophosphorus, if you remember the formula of orthophosphorus, hypo will be one less of that, right? Pyrophosphorus is actually double of this thing, right? Okay, so that will be 2 oxygens plus 2, you add 2 hydrogens here and 2 oxygens here. I am teaching you from ortho perspective, right? From ortho perspective. So these are the 3 things. Now let us talk about orthophosphoric acid. That is H3PO4, right? Now you have H3 and PO4. If you talk about the hypophosphoric acid, right, what will happen here? This is hypophosphoric acid. Now you remember what is orthophosphoric acid? This is your pyrophosphoric acid. Pyro is actually 2 phosphorus plus you have added 2 oxygens here, you have added 1 hydrogen here, right? Then if you talk about meta is basically the polymeric state here, and hypophosphoric is same as this one, is same as pyrophosphorus acid. It's just having 1 more extra oxygens here. So this is how you can remember these all oxo acids. Best, so they will not ask you this thing, right? Preparation, so they will definitely not ask you, right? But what they can ask you is the characteristic bond. Oxidation state you can already form. What you need to remember is the name and the formula, right? This is, I would say, they can ask you this, right? Okay, so how you can remember this? Relating to each other, right? Okay. Now, next one is, but if you ask me, man, will they ask us, like when we talk about P block, ma'am, is this important? It's not that important, right? That's why I'm like just telling you that you can remember that. That's totally your choice. But name is what you need to know, right? Okay. So now, next is, in oxoacid phosphorus is tetrahedrally surrounded by 4 atoms. All these acids contain at least one P double bond O, one POH bond, as we have seen. The oxoacids in which phosphorus has lower oxidation state contain, in addition to this and this, either P and P bonds but not both. Wait a minute, lower oxidation state less than +5 contain, in addition to P double bond O, POH bonds, either PP or they contain but not both. So they are saying that if you talk about the oxidation states here, which are less than +5, right? So here it is less than +5. Here it's also it is less than +5, which contains 2 phosphorus, then it will also have PP bonds, right? Okay. Then the acids in +3 oxidation states of phosphorus tend to disproportionate to higher and lower. So if you talk about the acids which are having +3 oxidation state, like this one, right, it will disproportionate, right? So like you have H3PO3, it is going to disproportionate into H3PO4 and PH3, right? Okay. For example, orthophosphoric acid. Basically, this acid is also the most important. One is H3PO3. If you ask now which acid you will see frequently, one is phosphenic acid, then phosphonic acid. These are the 2 acids which you will see very frequently in your chemistry. Rest of the acids you will not see very frequently, but these 2 acids you will see frequently. So the oxidation number of these 2, the structure of these 2 becomes automatically very important for you, right? Okay. Next we have the acids which contain pH bonds have stronger reducing properties. So now see, if you have pH bond, that means this hydrogen it can lose, right? What is reducing power? That means to reduce the, basically they are leaving the hydrogen here, right? So basically they are itself getting oxidized. If someone having good reducing power, they will themselves get oxidized. Oxidation means the removal of the hydrogen. So if they have pH bond, then they can remove hydrogen, right? So acids which have pH bonds, hypophosphoric acid is a good reducing agent as it contains pH bonds. That is why this you have used in organic chemistry, we have used this thing as a good reducing agent in so many things, right? Okay. AgNO3 to metallic character, right? We have also seen that how we had benzene diazonium chloride, it was reduced to hydrogen by H3PO2, right? Okay, so these are the applications, right? Then you have these pH bonds are not ionizable to give H positive and do not play any role in basicity, right? Only, now very important thing what they are saying, that is a good reducing agent. It contains 2 pH bonds reduce, right? Now these pH bonds, only those hydrogen atoms which are attached with oxygen in the POH form are ionizable, right? Because of this, the N factor will change. Because of this, the N factor has changed, right? That is why this paragraph also becomes important for you, right? These pH bonds are not ionizable to give H positive and do not play any role in basicity. But if you talk about hydrogen atoms that are linked to oxygen, they will play the role in basicity. Thus, H3PO3, right, and H3PO4 are dibasic and tribasic. So let us see that H3PO3, H3PO3. This is H3PO3. Now you have 2 OH bonds. That is why its basicity or its N factor is 2, right? If you talk about this one, here you have 3 OH bonds. That is why the basicity is 3. That means the N factor or the valency factor is 3 here, right? Okay, that is why I'm telling you that these two are important, right? These two are important and this one is important, right? Here it is monobasic. Here N factor is 1, right? Okay. Next is, yes. Okay, so that was about, this paragraph is important for you. Okay, understood? And this thing is also important, that H3PO2 is a good reducing agent, right? Okay, that is why we have used this, right? In organic chemistry, we use this as a reagent. Right? Okay, guys. Okay, guys, everybody. Yes or no, everybody in the chat box. Now we have group number 16. I really doubt that will we be able to complete group number 16 today or not, right? But we will do that in tomorrow's lecture, because group number 17, right, the properties are not in your syllabus. You don't have that many compounds. Group number 18 is also very small. So rest of the part we will do in the next lecture. But today let's see the properties. Let's not see the compounds here, because compounds are eventually not very important for you, right? Important thing is the exceptions. Compounds I am teaching you so that you can know that what to do and what not to do, right? Okay. What I am asking you to do is the maximum that you need to do, right? So group number 16 elements: oxygen, sulfur, selenium, beryllium, polonium. These are the constituents. So oxidation, right? So this become your group number 16. The name is derived from the Greek word brass and points to the association of sulfur and its congeners with copper. Now they are saying that this group is known as chalcogens, right? This group is known as chalcogens. Most copper minerals, because it forms different alloys, most copper minerals contains either oxygen or sulfur, and frequently the other members of the group. Because copper contains these things, that is why it is called as like chalcogens, right? Now next thing is oxygen. Okay, first we are talking about the oxygen, that is the most abundant thing here. Is it? Yes. Before that, let us see the oxidation state, that is NS2NP4, right? So the lower oxidation state will be +2, higher oxidation state will be +6, lower will be +4. That is the two oxidation state that it can have, right? Now let us see the oxygen here. Oxygen is the most abundant. Obviously, we breathe oxygen, we require oxygen, right? On Earth, oxygen forms 46.6% of Earth crust. Dry air contains 20.9.4% of oxygen by volume. However, the abundance of sulfur in the Earth crust is only 0.03 to 0.1%. Combined sulfur exists primarily. Now we have talked about the abundance of oxygen. Sulfur is also very important for us. We also use sulfur. Exists primarily as sulfates such as gypsum, right? So gypsum. Then we have Epsom salt, right? Important these are, okay? Then you have barite. Then you have sulfides such as galena. Then you have zinc blende. Then you have copper pyrites, right? Okay, traces of sulfur occur as hydrogen sulfide in volcanoes. That's not important. Organic materials such as eggs, proteins, garlic, onion. Why you cry when you cut onion, right? Why you have some people actually, the smell of the onion and also the smell of this garlic is very irritating to them. Why? Because of the sulfur that is present in it. Mustard, hair and wool contains sulfur. In all of this, you have the presence of sulfur, right? Okay. Sana, Vula, okay. Check, relax. Okay, I'll ask the team about it. right? Don't spam here, don't spam, right? Selenium and beryllium, now these are not usually found, are also found as metal selenides and pteralides in sulfide ores. Polonium occurs in nature as decay product of thorium and uranium mineral. Polonium, otherwise it will not occur. The important atomic and physical properties of group 16 along with electronic configuration is written here. So you'll see the properties over here, right? The general electronic configuration is this one, right? Due to increase in the number of shells. See, same thing we are repeating again. Down the group shells are increasing, right? Atomic and ionic radii increases from top to bottom. The size of the oxygen atom is, however, exceptionally small, right? This is important. The size of the oxygen atom is exceptionally small. Ionization enthalpy decrease down the group definitely as size is increasing. That is why ionization energy is opposite to size. It will decrease. It is due to increase in size. However, the elements of this group have lower ionization energy as compared to group number 15. Can you tell me the reason? Reason is because group number 15 elements, they had NS2 NP3. Now they have NS2 NP4. See, after losing one electron, it will become NS2 NP3, which is a stable state. So group number 16 wants to lose the electron, but here it will become NS2 NP2. Here this state is more stable. That is why it does not want to lose the electron. That is why group number 15 has more ionization energy in the corresponding periods. This is due to the fact that group number 15 elements have extra stable half-filled p orbital electronic configurations. Because of the compact nature of oxygen, I am saying oxygen is exceptionally small, very, very small it is, right? It has less electron gain enthalpy, right? Now, oxygen is very small, exceptionally small. So when, for example, you are living at a very small place, you have a very small house, right? So now would you want your 30 relatives to come in your that 2 rooms and occupy everything and ruin your studies? You don't want that, right? You want that, okay, mom, dad, please don't invite any relatives to the house. Why? Because I want to study. They will ruin my study. They will stay in these rooms and they will gossip about everything. Same thing will happen with oxygen. It's a very small, it's very small molecule. That is why it's not able to occupy another more electrons, right? No doubt it is electron negative, but its electron gain enthalpy is very high, right? It's very less electron gain enthalpy. That means electron affinity, right, is very low, right? Okay. However, from sulfur onwards, the value again becomes less negative up to polonium. So maximum is of sulfur. Sulfur wants to gain. Next to fluorine, oxygen has highest electronegativity. Its electronegativity, that means in a bond, it wants to pull the electron towards itself. That is shared pair of electron it is pulling. Value amongst the elements within the group, electronegativity decreases with an increase in atomic number. This implies that metallic character increases from oxygen to polonium. So see, very simple thing, that down the group, your electronegativity decreases, metallic character increases, right? Okay. But if you talk about the electron gain enthalpy, for sulfur it is less negative, right? Okay. Do you know the concept of electron affinity and electron gain enthalpy that we have done in classification, right? Do you remember that concept, or do I need to simply shut the door? Do I need to again tell you that what is electron gain enthalpy and affinity? Affinity, you can say that the hunger that I have to eat food, right? And electron gain enthalpy is how much food I am eating, right? Okay, that is the two differences, right? And they will have opposite sign to each other, right? So if they are saying that it is less negative electron gain enthalpy, if I am saying this is -7, then this, so it is -5, that means what I am saying, it has more, this is -7 and this is -5, right? Less negative we are saying. Otherwise, electron gain enthalpy and affinity are the same thing only. It's just that the signs are opposite to each other, right? Okay. Okay, guys, negative just symbolizes negative, positive. Negative, when you talk about electron affinity, right? I am very hungry, right? I have positive. Positive means I want to have that. I want to have that food, right? So electron gain enthalpy for that thing will be negative, right? Okay. Yes. Now, some of the physical properties of group 16 elements are given in the table. Oxygen. So now let us see firstly the table only. Let us see the table only firstly. Where is this table? This is the table that you have. Right? This is the table that you have. So as you can see here, this is oxygen, sulfur, selenium, tellurium, polonium. So now let us see that. Atomic number we know, atomic mass we know, electronic configuration we know, right? That here 3d electrons and 4d, then 4f and 5d electrons are getting added. If you talk about the covalent and the ionic radius, firstly let us talk about it. It is increasing to a very high rate when we talk about from oxygen to sulfur. Then it is increasing but to a very less rate. So size is increasing definitely, but from oxygen to sulfur, this is like a very large gap that you can observe, right? A very large gap. Then if you talk about ionic radius, it's the same thing. Then you talk about electron gain enthalpy. Now this is the thing that I was telling you. So this is -141. Now for them, sulfur has the maximum negative electron gain enthalpy, right? As compared to the others. Firstly, it will firstly increase, the negativity will increase, then it will further decrease, right? So sulfur will be the highlighted point here, right? Then we have ionization enthalpy. It is definitely decreasing, decreasing, decreasing. So there is no exception in that. Then electronegativity, as you can see, it is also decreasing, 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 right, down the group. Density, as you can see, it is increasing down the group, right? Melting point, it is also, firstly it is increasing, increasing, increasing. Then to polonium, it is decreasing. So you can see a variation here. You can see a variation in this part, right? In this part, you can see a variation that it is decreasing, decreasing, decreasing. Then it is, firstly it is increasing, 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 then it is decreasing also. With boiling point, it is increasing, 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 and then again it is decreasing, right? So it's the same trend they follow for melting and boiling point. Oxidation states we will talk about, right? Okay, so that's the same trend that they are following here. Let us see the theory part here. This done. Okay, oxygen and sulfur are non-metal. Selenium and beryllium is metalloid, whereas polonium is a metal. Polonium is radioactive, right, as I told you, right, and have a short-lived, very short life radioactive element. All these elements exhibit allotropy form. They exist in allotropic form also. The melting and boiling point increase with increase in the atomic number down the group. In general, they are telling about, but in the last, it will decrease also, right? The large difference in melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic and sulfur exists as polyatomic. So if you see this, the large gap that you can see here from 50 to it is 393. Then it is also increasing but to a smaller rate, right? So this large gap is due to that it is existing as O2, it is existing as S8. So it is difficult to break a S8 molecule. It is having a crown kind of shape. It is difficult to break that molecule as compared to O2, right? Because it is having only 2 bonds here, right? Then oxidation states and trends in chemical reactivity. So if you see this here, the elements of group 16 exhibit a number of oxidation states, right? The stability of -2 oxidation state decreases down the group. -2 means to gain 2 electrons. So it has Ns2Np4. If it gains 2 electron, it will become Ns2Np6. Now they are saying it is decreasing down the group, because down the group metallic character is increasing. They want to lose the electron. They don't want to gain the electron. That is why this gaining of electron will decrease down the group. Polonium hardly show -2 oxidation state. Some electronegative oxygen is high. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, right? We know that oxygen is very, like we see oxygen as -2, we give it, even the oxidation number, usually we write it as -2. Why? The oxidation, the electronegativity of this oxygen is very high. That is the reason. Okay? Okay. In the case of OF2, now this is peroxide they are talking about. In the case of OF2, where its oxidation state is +2, right? Now, why? Because fluorine is more electronegative as compared to oxygen, right? So that is the reason. Other elements of the group +2, +4, +6 oxidation state, but +4 and +6 are more common, right? Other will show this, right? So now +4 and +6 are more common states. Sulfur will usually show +6 only. Sulfur, selenium, tellurium usually show +4 oxidation state in their compounds with oxygen, +6 with fluorine, right? +4 with oxygen and +6 with the fluorine. For example, SF6, they will show 6 oxidation state. SO2 with oxygen, sulfur is showing +4 oxidation state. The stability of +6 oxidation state decreases down the group, because see, lower oxidation state stability increases down the group, right? Bonding in +4 and +6 oxidation state is primarily covalent, right? Okay. Okay, guys. In case of OF2, wait a minute, this we have done, right? This we have done. Then you have this thing also we have done. Then you have anomalous behavior. Wait a minute. Why this anomalous behavior? Same thing, because of is due to its small size, high electronegativity, right? And one typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding, right? Now water has a very strong hydrogen bonding which is not found in H2S, because oxygen is more highly electronegative. Smaller the size, more will be the electronegativity, that we have already seen. Smaller the size, more will be the hydrogen bonding, that we have seen in hydrogen bonding, right? So the absence of d orbital, this is another factor, right, in oxygen, limits its covalency to 4 and in practice rarely exceeds 2. So d orbital, see, you have never seen +3 oxidation, +4, +6, so never. You seen +2, maybe -2, +1, -1. These oxidation state we have seen for oxygen, not +4, +6. Why? Because covalency it cannot expand, right? On the other hand, okay. Now let us talk about the reactivity with hydrogens, right? Okay. Reactivity with hydrogen. It will form halides. All the elements of group 16 form hydrides. Now what kind of hydride? E is existing in usually +4. This is O negative. So it, sorry, this is H positive. Wait a minute. E, they are showing the usual oxidation state as +4 or what thing? +2, right? +2 oxidation state. Okay. Now, all the elements of group cysteine form hydrides, which is H2E, right? You have seen H2O, you have seen H2S, H2SE, H2TE, H2PO. Some properties of hydrides are given in table 7.7. The acidic character, now let us see this. The acidic character increases from, again the same thing, okay? Acidic character will increase. Acidic character, the increase in acidic character can be explained in terms of decrease in the bond enthalpy for the dissociation. See, down the group size is increasing, right? So that is why as the size is increasing, down the group bond length is increasing. That is why bond dissociation enthalpy is decreasing. This is what they are telling you. Explained in the decrease in the bond enthalpy. Why? Because of increase in size. So as the bond enthalpy is decreasing, it is difficult, it is easy to lose the hydrogen, right? So that is why acidic character increases down the group. Understood? Acidic character decreases down the group. Why? Because this is hydrogen, this is oxygen. This is hydrogen, this is that element. Down the group size of this element is increasing, bond length is increasing. That means bond enthalpy is decreasing. It is easy to break this bond. More easy to break this bond, more acidic it will be. More easily it can give H positive, right? So that will be the reducing power, right? So owing to the decrease in enthalpy for the dissociation of He down the group, the thermal stability of hydrides also decreases. Why? Because definitely if your bond is stronger, that means you have more stability. The bond is more stable. So more will be its thermal stability, right? All the hydrides except water possess reducing property, and this character increases from H2S to H2. Now they are saying that H2S will not possess reducing property because of hydrogen bonding. The bonds, the hydrogens are already occupied in the hydrogen bonding, so they don't have power for the reduction, right? That is why the reducing property also increases down the group, right? Okay. So I can write one thing here, right? As you can see here, right? What you can see, that melting point, right? Melting point and boiling point has a different behavior that we need to note down. Then for He distance, right? Distance is obviously increasing. That is why bond dissociation enthalpy is also decreasing, because the distance is increasing. The bond of formation is also, this you don't need to remember, right? HEH, that is bond angle, right? It is also decreasing down the group, because as the size is increasing, there are less repulsions. Lone pair na. See, you have oxygen, you have H, you have H. This is your lone pair, this is another lone pair. If the size is smaller, there will be more repulsions. Bond angle will be more. If you have increased the size, lone pair will be away from each other, right? If you have more size, if it has, this atom has more size, this is lone pair, this is lone pair, they are away from each other. So that is why less repulsions they will have. That is the reason they are saying bond angle will decrease because of less repulsions, right? Then dissociation constant, you don't require. These three things are important, right? So now I can write which thing increases, which thing decreases. Firstly, let us write what about the melting point, right? Then we will write which thing increases, which thing decreases. Boiling point, we can say that it is, maximum is for water, H2O. Then you have H2TE. Then you have H2SC. Then minimum is for H2S, right? So basically, why water has maximum boiling point? Because of the hydrogen bonding, right? Otherwise, so it is increasing only down the group. Down the group, it is increasing only. Boiling point is increasing only. Why? Because down the group interactions are going to increase, right? So down the group boiling point is increasing only. But water has exceptionally high boiling point because of the hydrogen bonding, right? Because of the hydrogen bonding. If you talk about melting point here, this is the melting point. Now again, what you can observe here, it has exceptionally high, otherwise it is increasing only. Same reason, hydrogen bonding and symmetry, right? So it will be same, that first you have water, then you have beryllium, then you have selenium, then you have sulfur, right? Polonium, why we are not studying polonium? Because that is a radioactive element. That's why we are not studying that. So let us see which increases down the group, which are the things that decreases down the group, right? Because tables, so obviously you can't remember, right? You just need to remember these things, right? Now, increases, first thing is acidic character and reducing power is increasing, right? Okay, acidic character, you can write here, acidic character, acidic or reducing power is increasing down the group. Reason why it is increasing down the group, acidic character, because it can give H positive there. Down the group it can give H positive, right? Because of the less, it can give, what is the reason I told you? Hydrogen bonding will be there in this one, because of that. Now why it is decreasing? Why it is decreasing down the group? What are the things that are decreasing? Thermal stability. Bond length, forgot. Bond length, है ना? Thermal stability, it is decreasing down the group. Why? Because bond length is increasing. Bond length is increasing. Here you can say that bond length is increasing, right? Okay, bond length. Then thermal stability is decreasing. Then you have basicity is opposite of acidity. What else? What else? What else they have mentioned here? Bond length we have done. Bond length we have done. Thermal stability we have done. Reducing property we have done. Yes, I think that's it. Right? Acidity and basicity and thermal stability will decrease down the group. There was also one more thing. I must have written it here. Yes. Stability, bond angle, yeah. Bond angle, okay? Third thing was bond angle. That also decreases down the group. Bond angle is also decreasing. Dissociation energy is also decreasing. Dissociation energy is also decreasing down the group. Right? Okay? Understood? Yes, this is what you need to remember from hydrides of group number this. Okay, guys? This is what you need to remember here. Then rest of the part we will do in the next class, because so much we are left with. Definitely we can't complete all of that in today's lecture, right? It's not possible. So rest of the group 16 and group 17 and group 18 we will do in the next class, that is tomorrow at 5 p.m. and that is going to be a long class. I'm going to tell you that is going to be a long class, okay? So be prepared tomorrow, right? Okay, at 5 p.m. I'm going to take the class. So keep your slot free for tomorrow, because tomorrow we are going to end chemistry will be done. Then we are just left with practical chemistry, that too you can do, right? We will do that. I mean, I'll teach you, right? Practical chemistry, I'll teach you after maybe 15-20 days, right? Okay. Yeah. Okay, then before going, one important thing for you guys. Wait a minute. One important thing for you guys here. Because, I don't know. I hope so you are able to see this now. Okay, I think so that you are able to see this now. Is it or not? Now, guys, this is your full NEET preparation. Get complete NEET preparation treasure box. You just need to click on this link here, right? Wait a minute. You just need to click on this link here, and what you will get, wait a minute, guys. Just give me a minute. Now, what you need to do, you just need to click here, right? And here you will get bio, physics, chemistry, right? You will get the YouTube link of individual chapters, right? Then students, you will also get, wait a minute, you will also get class notes, right, of these, and you will get the previous year question test, the previous year question chapter wise PDFs, right, from CBSE, NEET, and also your NCERT solutions are available for these chapters. Okay, so everything you are going to get totally for free of cost, right? So don't waste your time, just click on this and avail this thing that is totally free of cost for you, right? Again, how many of you have done biomolecules test? I have given you this last what we have done in the last lecture of P block. I have given you this test. Have you done this or not? No? No, ma'am, we have not done that. Why you guys don't do the test that I give you? Okay, so do the test that I give you. Now, the next test, give the test for chemical bonding. Okay, previous year question, chemical bonding test is your next test. Do tell me the results for that. Yes? Okay, then, bye-bye, guys. Okay, superstar, now we have completed the syllabus. Now we will do revision and problem solving only, right? So tomorrow is going to be your last theory lecture, like proper detailed theory lecture. Okay, chalo. Okay then, bye bye. I'll see you tomorrow at 5 p.m. Bye bye. Take care. Bye bye. See you all.